Welcome back to the deep dive. Today we're not just scratching the surface. We're going all the way down, right down to the bedrock of how artificial intelligence actually processes information.
Mm.
We've got a stack of research here that tackles what I think is one of the most frustrating and sort of invisible bottlenecks in the entire AI industry right now.
It's a bottleneck that, most people don't even realize it's there. Not until they try to use an AI for something genuinely complicated and it fails.
Exactly. We're not talking about, robots taking over the world today. We're talking about something much more mundane, but I'd argue it's way more important. It's the problem of the missing forest.
Forest for the trees problem.
Yes. You know that feeling when you're reading a really dense contract or a technical manual or even just a complicated novel? You see the words, you get the sentences, but if you can't hold the entire structure of that document in your head at once, you miss the big picture.
You miss the theme.
You miss the theme. You miss how page 5 connects to page 500.
And that is precisely where modern AI, specifically this technique we call retrieval augmented generation, or, RAGN, it just falls flat on its face. It sees all the individual trees, but it is completely blind to the forest.
So today we're diving deep into a really fascinating paper. It's from a team at Stanford University. The title is a bit of a mouthful, so just bear with me here.
Okay.
It's called RAPTOR, Recursive Abstractive Processing for Tree Organized Retrieval.
It is a heavy title, but you have to admit, RAPTOR is a great acronym. It sounds kind of predatory.
It does. It sounds like it's going to hunt down the information you need. And honestly, after reading this paper, it kind of does.
It does.
So the mission of this deep dive is to explain exactly how RAPTOR works, why it represents this total paradigm shift from the search methods we're all used to, and why this might be the key to unlocking AI that can actually read.
Not just scan for keywords.
No, but read and comprehend like a human expert.
It's a shift from seeing a text as just a flat line of words, from start to finish, to seeing it as a three-dimensional structure, a literal tree of knowledge.
I want to start where the paper starts, because they use an analogy that is just perfect for this. They open with a fairy tale, the Cinderella problem.
This is the absolute best way to visualize the limitation we're dealing with in all the current tech.
So picture this. You have your standard off-the-shelf AI, maybe it's a chatbot you use for work. You've uploaded the entire text of the original Cinderella story into its database.
Okay.
And you think, great, now it knows the story. So you ask it what seems like a dead simple question. How did Cinderella reach her happy ending?
A question any 5-year-old could answer in a heartbeat. They'd say, well, she was nice and she had a fairy godmother and she went to the ball and then she lost a shoe.
Exactly. They'd give you the whole arc. It's a chain of cause and effect. But if you ask a standard RGAD system this question, it often just panics. It gives you this weird, disjointed answer.
We should probably pause and clarify why it panics. For anyone listening who isn't, building large language models in their garage, let's just quickly unpack what standard RAG is even doing.
Good idea. Let's do the explain like I'm 5 on RAG.
So think of a large language model like a GPT-4 as this genius student who has to take a final exam. But the exam is on a book they haven't actually memorized.
Okay.
RAG is basically giving them an open book test. When you ask a question, the AI frantically flips through the book, finds a few paragraphs that look relevant, reads just those, and then tries to write an answer.
That sounds fine, though. I mean, that's how I take tests. That's how I do research.
And it works great for specific isolated facts. If you ask, what color was the shoe? The student scans the text, finds the sentence, the shoe was made of glass, and writes that down. Boom. Easy.
Right.
But for a question like, how did she get a happy ending? That whole approach just breaks down.
Because happy ending isn't a single fact on a single page. It's the result of the entire book.
Exactly. The student starts scanning for keywords, like happy ending. They might find the very last sentence of the book, and they lived happily ever after.
Okay, so it grabs that little chunk.
Then maybe it grabs a random sentence about a pumpkin turning into a carriage. Just because that sentence mentions happiness or magic or something, it retrieves these little disconnected chunks of text.
But it misses the connective tissue. It misses the why.
Yes. It sees these isolated puzzle pieces, a shoe here, a pumpkin there,
Yeah.
a wedding, but it has absolutely no idea how they fit together to make the picture on the box.
Because standard RAG just retrieves fragments. It chops the book into these little distinct blocks and retrieves them based on a kind of keyword matching. It doesn't see that the pumpkin was necessary for the ball, which was necessary for meeting the prince, which was the whole chain of events.
That is the Cinderella problem. Standard retrieval is myopic. It's incredibly short-sighted. And when you apply that same problem to, say, a 100-page legal contract or a dense scientific paper, that myopia becomes actually dangerous.
You miss the contradiction on page 50 that completely invalidates the clause on page 5.
Right.
So enter RAPTOR. The team at Stanford looked at this whole situation and basically said, we need an AI that builds a mental model of the text just like a human does.
They proposed moving from this flat list of text chunks to a hierarchical tree structure.
A tree of knowledge. I love that image. So let's break this down into 3 main parts so we can really get it. First, section 1. The core problem, we really need to dig into why this chunking thing fails us so badly.
Okay.
Section 2. The high-level intuition. How on earth do you build this tree? And then section 3. The methodology, deep dive, step by step. How does the machine actually do this?
And we'll finish up with the results. Does it actually work? Spoiler alert. The numbers are pretty wild.
Let's start with the problem then, because the paper makes a really interesting point about misleading context. I actually flagged this in my notes. They essentially say that reading a snippet out of context isn't just unhelpful. It can be actively deceptive.
Oh, absolutely. Think about a technical manual for a really complex piece of machinery. Imagine you use a standard search to find shutdown procedures. It pulls up a sentence that says, the system will shut down automatically.
Okay. Sounds like a safety feature. I'd read that and think, great, I don't need to do anything.
But the sentence immediately before it, which the AI didn't retrieve because it was in a different chunk, might have been if the cooling fans fail catastrophically.
Ah. Oh, wow. So the context flips the meaning completely. It's not a feature, it's a crash.
Exactly. Standard rag chops documents into these little segments, usually about 100 words long. It's like slicing a loaf of bread. If you slice that manual, you might physically separate the condition, the fans failing, from the consequence, which is the shutdown.
You have 2 slices of bread, and the AI only hands you one of them.
Yes. And suddenly you have an AI telling you the system just shuts down on its own. Or, even worse, telling you everything is fine when your server room is literally on fire. Right. But the even bigger issue RAPTOR goes after is what the paper calls the thematic question.
Give me an example of a thematic question.
Something like, how does the author's argument evolve from the introduction to the conclusion? Or, what is the central conflict in this story?
You physically cannot find the answer to that in a single 100-word slice. It doesn't exist there.
No, it doesn't. The answer is distributed. It's spread out across the entire document. The answer exists in the relationship between the slices, not within the slices themselves.
That's a key insight right there. The answer is in the relationship. Standard retrieval treats every single paragraph like it's an island. It doesn't build any bridges.
Precisely. And humans, we don't read like that. When you read a book, you don't just memorize sentences in a row. You abstract. You finish a chapter and you think to yourself, okay, that was the chapter where the hero learns to trust his team. You compress 20 pages of detail into one single high-level concept.
I build a hierarchy in my head. I have the big ideas, and then under those I have the plot points, and under those I have the specific dialogue.
You do. Everyone does. And RAPTOR is trying to force the AI to build that exact same hierarchy. It wants to capture both the high-level themes and the low-level granular details all at the same time.
Okay, so let's move to section 2 and really try to visualize the solution. The paper talks about a tree. Help us see this.
All right, imagine a library. But let's say it's a messy, disorganized library where some prankster has come in and they have torn every single page out of every single book and scattered them all over the floor.
That is my worst nightmare. My organizational soul hurts just hearing that.
Laughs it. It's you. But that disorganized floor, that standard rack, just a floor full of loose pages. You have to run around picking up random pages to try and find an answer.
Okay, chaos.
Now, imagine we decide to organize it. We start picking up the pages. That's the bottom level of our tree, the leaves, the raw text. We read pages 1 through 10. We realize they're all about the same scene, so we group them together. And then we write a little sticky note that summarizes them. Something like Chapter 1, The Arrival.
Okay, so now I have a layer of sticky notes kind of hovering above these little piles of pages.
Exactly. Then we look at the sticky notes. We take the summaries for Chapter 1, Chapter 2, and Chapter 3. We realize they form the first act of the story, so we group those sticky notes together, and we write a bigger sticky note.
Part 1. The hero's journey begins.
Something just like that. That's another layer up. We're getting more and more abstract.
Right.
And we keep doing that. We group the part 1 note with the part 2 note until we have one final, single sticky note at the very top that summarizes the entire book, a story about redemption and forgiveness.
So it's a pyramid, or I guess an inverted tree with the root at the top and all the leaves at the bottom.
It's a pyramid. And remember, RAPTOR stands for Recursive Abstractive Processing for Tree Organized Retrieval. The key word there is recursive.
And recursive just means you're repeating the same process over and over, right? It's a loop.
It's a loop. You summarize the text, then you summarize the summaries. Then you summarize the summaries of the summaries. You just keep going up until you can't go any higher.
It sounds so elegant. It sounds like how I wish my own brain organized information all the time. But as always, the devil is in the details. So I want to get into section 3, the methodology deep dive. Because the engineering choices they made here are really, really clever, and they solve some very specific problems.
They are. The authors, Parthasarathy and his team, they didn't just throw an LLM at a wall of text and hope for the best. They used some very specific techniques to make sure this works.
Let's walk through it step by step. Step 1 is segmentation, creating the leaves.
Right, the very bottom layer.
The paper mentions they split the text into chunks of about 100 tokens.
Which is roughly 75 words, a short paragraph.
But there's a specific detail here that really caught my eye, and I think it's critical. They talk about sentence integrity.
Oh, this is huge. It sounds super technical, but it's actually just about basic grammar. Most of the basic text splitters out there, they just count to 100 and chop.
Right.
Doesn't care if you're in the middle of a word or in the middle of a sentence.
So you get a chunk that ends with the quick brown fox jumps over, and then the next chunk just starts with the lazy dog.
Exactly. Now, imagine you're the AI and you're trying to understand that first chunk. The quick brown fox jumps over. It's a cliffhanger. It's semantically incomplete. Who did he jump over? Why?
And in the world of AI, we turn text into these things called vectors, basically, numbers that represent meaning.
Yes. And the vector for half a sentence is a confusing vector. It's just noise. It doesn't point to a clear concept like jump or fox. It points to this murky, useless middle ground.
So how does RAPTOR fix it?
RAPTOR does it differently. It uses what's called a regular expression. It's basically just a code rule to check for sentence boundaries. If that 100th token is in the middle of a sentence, it moves the entire sentence to the next chunk.
It respects the period.
It respects the thought. It makes sure that every single leaf on the tree is a coherent, complete idea. It's like building a house with whole bricks instead of just using broken rubble.
That seems like such a small detail, but I bet it makes a massive difference in the overall data quality.
Oh, it absolutely does.
Yeah.
You know, garbage in, garbage out is the golden rule of AI. This is a step to ensure quality in.
Okay, so we have our clean leaves. Now for step 2, clustering. Building the branches. This is where I think RAPTOR really diverges from just, reading a book in a straight line.
Yes. This is where it gets really smart. In a physical book, page 5 is right next to page 6. That is temporal ordering. It's based on time or space.
Sure.
But does the information on page 5 actually relate to page 6? Well, maybe. But maybe the information on page 5 actually relates to a clue that was dropped way back on page 200.
Like in a mystery novel. The murder weapon gets mentioned in passing in Chapter 1, but it's not relevant again until the big reveal in Chapter 10.
Exactly. If you only group things by proximity, just grouping neighbors, you miss that connection completely. You create a cluster for Chapter 1 and a separate cluster for Chapter 10, but you never link the weapon to the killer.
Yeah, what does RAPTOR do?
RAPTOR uses a clustering algorithm. It looks at the meaning of the chunks, not their page number.
So it's creating these buckets of related information regardless of where they happen to live in the original document.
It completely ignores the page number at this stage. It uses the vector embeddings, those mathematical GPS coordinates of meaning we talked about. It just asks, which of these chunks are mathematically similar to each other?
So if chunk A is about the silver dagger on page 5 and chunk B is about the silver dagger on page 200, RAPTOR says, you two, you belong together.
Exactly. It physically reorganizes the book based on topics. The paper calls this soft clustering.
Soft clustering, as opposed to hard clustering. That sounds like a mattress firmness rating.
It kind of does. In hard clustering, a chunk can only belong to one bucket. It's binary. You are either in the physics bucket or you're in the chemistry bucket, period.
But the real world is messy. Concepts overlap all the time.
Precisely. Physical chemistry is a thing. Or think about a news article about a trade war. Is that economics or is it politics?
It's both.
It's both. RAPTOR uses something called Gaussian Mixture Models. It's a type of probabilistic model that allows a single chunk of text to belong to multiple clusters at the same time.
Oh,
It can sit in the economics bucket and the politics bucket simultaneously.
that is incredibly flexible. It really mirrors how our brains work, doesn't it? We associate ideas in multiple directions. I can think of the word apple and immediately associate it with fruit and technology at the same time.
It does. And the ablation study in the paper, that's where they test different features to see what really matters. It proved that this clustering approach is far, far superior to just grouping neighboring sentences. It captures what they call homogeneous content.
Homogeneous meaning of the same kind, so it creates these clusters that are actually about the same thing, not just things that were near each other.
Correct.
Okay, so we've grouped all the related ideas. Step 3 is summarization. This is where we bring in the LLM.
Right. We take that bucket of related text, say 5 different chunks that are all about the silver dagger, and we feed them to the LLM and tell it, summarize this.
And this creates a new piece of text, a parent node for the tree.
Yes. And this is where we have to address the elephant in the room.
Hallucinations.
Hallucinations. When you ask an AI to summarize, sometimes it gets creative, it invents details, it adds some flavor text that wasn't actually there in the source.
And the authors were worried about this, right? I mean, if you build a tree out of lies, the whole structure just collapses.
They were very worried. They actually conducted what they called a focused annotation study. They had humans manually go through and check the summaries against the original source text.
And what was the verdict? How bad was it?
They found that about 4% of the summaries contained some kind of minor hallucination.
4% isn't zero? Is that a problem?
You'd think so, right.
Yeah.
But here is the fascinating finding. These hallucinations did not propagate up the tree.
How is that possible? If the foundation is cracked, shouldn't the whole house fall down?
Well, think about what happens during summarization. It's a compression process.
Yeah.
You're stripping away all the detail to get to the core theme, the main idea. Usually the hallucinations are just minor details, a slightly wrong date, a wrong adjective, maybe a poetic flourish that the AI added. When you then summarize that summary for the next level up, those minor details almost always get cut anyway because they aren't the main point.
I see. So the abstraction process itself acts as a filter. It kind of filters out the noise as you go up.
Exactly. The hierarchy cleans the data as it's being built. And because the retrieval process has redundancy, it can look at the summary or the original text. The whole system is incredibly robust. It doesn't break.
That is really reassuring. It's like it has a built-in self-correcting mechanism.
It does.
Yeah.
So we summarize the clusters, and then step 4, we just repeat recursion.
The growth.
We treat those new summaries as if they were the leaves.
Yeah.
We embed them, we cluster them again, and we summarize those clusters. We just keep growing the tree until we hit the root node at the very top.
And now we have a map of the information density of the entire document.
We have a view of the forest, that's the top nodes, and a view of every single tree, that's the leaf nodes.
But building the map is only half the battle. We have to be able to use it. We have to be able to ask it questions. Which brings us to section 4, retrieval strategies. How do we ask the tree?
Right. How do we actually traverse this thing? The paper proposes 2 distinct methods for this.
Okay, so strategy A is called tree traversal. This feels the most intuitive to me.
It's like climbing down a ladder. You start at the very top at the root node. You ask the AI, is this super broad summary relevant to my question? If it says yes, you look at its children, the next layer down.
You drill down.
You drill down. You calculate the similarity score at each level.
Yeah.
You pick the top few branches that look the most promising. Then you look at their children. You keep pruning away the branches that don't matter and following the ones that do until you get all the way down to the specific details at the bottom.
It's efficient. You don't have to read the whole library. You just follow the signs. It's like looking at a table of contents, then finding a chapter title, then a section header.
It is efficient, but it has a flaw. The paper points out that it's greedy.
Greedy. That sounds bad.
In computer science terms, a greedy algorithm is one that makes the best decision it can right now, without any idea what's coming later. The problem is, if it makes a wrong turn at the top level, if it thinks, oh, this question is definitely about politics, when it's actually about economics, it prunes that economics branch immediately.
And once you prune it, it's gone. You can't go back.
You can't go back. You're stuck going down the wrong rabbit hole, and you will never find the right answer.
That seems like a pretty big risk.
It is. And that brings us to strategy B, the collapsed tree.
The flattening. This one surprised me when I read it.
It sounds so counterintuitive, doesn't it?
Yeah.
You spend all this time and energy building this beautiful, multi-layered tree structure, and then you just flatten it. You take a steamroller
You
to
throw all the nodes, the root summaries, the middle layers, the leaf, text, everything into one giant pile.
one giant pile.
Oh.
You search everything at once.
But why? Isn't that super inefficient? Why bother building the tree if you're just going to flatten it? Why not just search the leaves like we used to?
That's the million-dollar question. And the reason is something the paper calls flexible granularity.
Okay, break that down for me. Flexible granularity.
Think about the questions you ask. Sometimes, the best possible answer to your question is a high-level summary. If I ask, what is the overall theme of this book? The best answer is literally the root node. The leaves don't have that answer.
Right. The leaves just talk about shoes and pumpkins.
But if I ask a different question, like what color was the car, the best answer is a specific leaf node. The root node won't care about the car color.
So you have answers living at different altitudes in the tree.
Exactly. By flattening the tree, you're putting all of those options, all those different altitudes on the menu at the same time. You let the math, the cosine similarity, decide which level of abstraction matches your question the best.
You don't force the system to climb down the ladder and potentially make a mistake. You just let it grab the best match, whether that's a forest view or a single tree view.
That's it, exactly. So you get all the rich context of the structure, because the summaries still exist, but you also get the speed and the flexibility of a flat search.
And does the collapse tree actually work better in practice?
The results show that this collapse tree method is often the winner. It avoids that greedy mistake of going down the wrong branch, but it still provides that rich summarized context that standard RAG completely lacks.
So let's talk about those results. Section 5, performance and comparisons. We've built the tree, we've flattened it. Is it actually better than the old way?
The results are stark. I mean, really stark. They compared RAPTOR against standard dense passage retrieval, or DPR, and a bunch of other state-of-the-art models.
Let's look at the benchmarks. They used quality and narrative QA.
Narrative QA is what it sounds like, answering questions about books and movie scripts. That's the Cinderella-type stuff. But quality is a beast.
Why is quality so hard?
It stands for question answering with long input texts, yes, or something roughly like that. It's a data set of very, very difficult multiple-choice questions that are based on medium-length passages. These aren't CTRL plus F questions where you can just find the answer. They require reasoning. They require you to read the whole text, hold it all in your head, and actually think.
And what was the score? What was the result?
When they coupled RAPTOR with GPT-4, they improved the absolute accuracy on the quality benchmark by 20%.
Ooh, hold on. Let's just pause on that number for a second. In AI research, people usually pop champagne for a 1 or 2% improvement.
Exactly. A 1% gain gets you a paper. A 2% gain gets you a promotion. A 20% gain is a generational leap. It's absolutely massive.
That implies that the underlying model, the GPT-4, was probably smart enough to answer the question all along. It just wasn't getting the right information fed to it.
That is the critical takeaway. The brain, the GPT-4, works just fine. The eyes, the retriever, were broken. RAPTOR gave the brain the right context to work with.
It's like giving a genius a well-organized dossier versus just giving them a box full of shredded paper. Of course, the genius is going to do better with the dossier.
There's another qualitative example from the paper that I just love. It goes right back to that Cinderella idea we started with.
Oh, right. The synthesized knowledge example. This was my favorite part of the whole paper.
It's incredible. They looked at what RAPTOR actually retrieved for the question. What is the central theme of the story?
How did it pull up?
RAPTOR retrieved a high-level summary node, and that summary node contained the phrase, "the power of human connection."
Was that exact phrase in the original story?
No. That's the key. That is the incredible part. The phrase, "power of human connection," was created by the LLM during the summarization step. It was synthesized from the underlying text.
That gives me chills. The AI created new language to describe a concept that was only implicit in the text, and then it used that new language to answer the user's question.
Meanwhile, standard retrieval failed completely because it just searched for the word theme and found nothing. RAPTOR found the concept because it had actually built the concept itself.
That is the difference between a search engine and a research assistant. A search engine finds strings of characters. A research assistant understands ideas.
Well put. It validates the entire methodology. The tree isn't just some sorting mechanism. It's a thinking mechanism.
Now, section 6. I can hear the skeptics or maybe the CFOs in our audience asking this question. This sounds amazing, but summarizing a whole library recursively, that sounds incredibly expensive.
Computational efficiency. It's a completely valid concern. Summarization uses tokens. Tokens cost money.
So do they need a supercomputer to run this? Do they need a warehouse full of GPUs?
They tested the build process on a consumer-grade laptop, specifically an Apple M1 Mac with 16 gigabytes of RAM.
Get out. The laptop I'm using to record this deep dive right
The
now.
very same. You do not need a massive server farm to build a RAPTOR tree.
But how does it scale? If I double the size of the text, does the time double? Or does it square? Does it just explode?
It scales linearly.
Explain that for the non-math folks.
It just means if 100 pages takes 10 minutes to process, then 200 pages will take about 20 minutes. The cost doesn't explode into 10 hours or something crazy.
Why not? I would think building a tree would get more and more complicated as it gets bigger.
Think about that pyramid structure again. The bottom layer is all the heavy lifting. That's summarizing the raw text. But once you summarize that bottom layer, the next layer up is only about 20% of the size, and the next layer is 20% of that. The tree gets narrower and narrower as you go up. The upper levels are computationally very cheap.
So the cost is front-loaded, but it's manageable.
Exactly. And that makes RAPTOR commercially viable. You could theoretically run RAPTOR on a company's entire internal documentation, all their Slack history, their Jira tickets, their Notion pages, without completely breaking the bank.
That's a good point. We're seeing these huge million-token context windows from companies like Google and Anthropic. Does RAPTOR make them obsolete? Or do they make RAPTOR obsolete?
That's the big debate in the field right now. Some people just say, just show the whole book into the prompt. But think about that needle in the haystack problem again. Even if you can fit the entire haystack in the window, the model's attention mechanism can still get distracted by all the noise.
It gets lost.
Structure always helps. Organized data always beats big data. RAPTOR provides that essential structure.
Okay, before we wrap up, let's talk about the assumptions. Every model relies on a few key assumptions. What is RAPTOR assuming about the world?
It's making 3 big bets. First, it assumes that long texts actually have a hierarchical structure to begin with.
That they have subtopics and themes and a logical flow.
Right. If you fed it a phone book, just a random flat list of names, RAPTOR wouldn't help you very much. There's no theme to summarize. The tree would just be this weird, pointless luft of names.
Fair. It needs a narrative or some kind of logical flow to work with.
Second, it assumes that the summarization process preserves the needle, that it doesn't accidentally throw out the most important fact.
That the compression is lossless-ish.
Right. If the LLM is bad at summarizing and it accidentally deletes the one key fact you needed, say the specific data contract expires, then the upper nodes won't have it. If you only rely on those upper nodes, you've lost the data.
That's the risk of any abstraction, I guess. You trade detail for clarity.
And third, it's assuming that the clustering algorithm grouping by meaning is better than just reading in order, which the ablation study proved is generally true, but you can imagine edge cases where the chronological order is the most important thing.
Like a strict timeline of events.
Exactly. In a strict timeline, jumping around by topic might actually confuse the order of operations. But for most knowledge tasks, the topic clustering wins, hands down.
This has been dense, but in a good way. We've gone from Cinderella missing her shoe all the way to a recursive tree structure that can run on a MacBook.
It's a remarkable progression, isn't it?
Let's move to the outro. I want to synthesize this for our listeners. What is the one thing they should take away from RAPTOR?
To me, the core takeaway is that RAPTOR represents a real maturation of AI. We are moving past the keyword match era. We're finally entering the comprehension era.
And comprehension requires structure.
It absolutely does. A pile of bricks isn't a house. A pile of sentences isn't a story. RAPTOR builds the house. It organizes the information before you even ask the question.
That's the key Blinkist insight for me. The intelligence isn't just in the answering part, it's in the indexing. The real work is done before the query is ever typed.
Yes. The understanding is pre-computed.
And why should our listener care? I mean, maybe they aren't out there building AI systems.
Because we are all drowning in information. We have too many emails, too many reports, too many news articles. We don't need tools that just say, here are 50 documents that match your keyword.
We need a tool that says, I read those 50 documents for you, and here's the trend. Here's the conflict. Here is the answer.
Exactly. This is the bridge to a true digital research assistant. RAPTOR is the architecture that finally makes that possible.
I want to leave everyone with a final thought. We talked about that example where the AI generated the phrase, power of human connection. It wasn't in the text.
Yeah.
So if systems like RAPTOR are creating summaries that contain insights not explicitly written in the original data, Are we moving toward an AI that can generate new knowledge just by organizing existing data in a better way?
That is the provocative question, isn't it? At what point does summarization cross the line and become interpretation?
And if the AI is interpreting, we're suddenly relying on its ability to see connections that we missed, which is exciting and maybe a little terrifying.
It's the frontier.
Indeed. But for now, just remember, the next time you ask an AI a question, think about the forest, not just the trees. It might just be climbing a raptor tree to find your answer. Thanks for listening to The Deep Dive.
See you next time.